Hello and a very warm welcome to this session where we are going to solve previous year questions of GATE Aerospace, particularly from strength of materials. Well, if you are wondering what exactly are we going to cover in strength of materials, see, structures, which is a very important subject in aerospace engineering, can be divided into two parts. One is strength of materials, another is vibrations. Okay. So in this particular session, we are going to solve PYQs related to strength of materials. Okay. Chalo. So I hope all of you are fine, and those of you who are preparing for GATE 2026, I hope your preparation is almost over, because in a few days you are going to write your GATE exams. So all the very best to you. And those of you who are preparing for 2027, 2028 or any other upcoming year, if you want, you can enroll in our batches for GATE Aerospace, because we have already started it. A lot of students keep asking us, when are you going to start GATE Aerospace? When are you going to start GATE Aerospace? So I would like to tell you that last year we started GATE Aerospace, a dedicated batch for GATE Aerospace. Okay, it's not combined with mechanical or civil, it is dedicated batch only for GATE Aerospace Engineering. It is in English, so that all the students, no matter what your language is, will be comfortable with our batches. Okay, chalo. So this is my Telegram group where students like you can come and ask me any questions. You can discuss among yourself, you can ask all your doubts. So if you want, you can join it by either scanning this QR code or searching this in your Telegram group. Okay. Is it beneficial for GATE mechanical? Yes. See, only a few topics are different in GATE mechanical and GATE aerospace when it comes to strength of materials. Okay, a lot of questions are relevant for you also. Okay. Chalo. So without any delay, let's begin our session. This is the first question from GATE 2009 Aerospace. Consider a simply supported beam of length 2L with an overhang of length L loaded by an end moment M as shown below. The bending moment distribution for this beam is, it's an MCQ. So which one of these options are correct? Is correct, sorry. You need to find the correct bending moment diagram of the beam. It's a overhang beam which is subjected to a couple M at the end. So how do you find the correct bending moment diagram? First of all, the point at which couple is acting, at that point the bending moment will have two different values, right? The bending moment will suddenly change. So this cannot be the answer and this cannot be the answer. Either A is correct or B is correct, right? There must be a sudden change in bending moment at the end. Secondly, from here to here, the bending moment has to be constant, right? The bending moment is not changing. If you consider a section here, bending moment will be M. If you consider a section here, bending moment will still remain M. So from this point to this point, the bending moment has to be constant. So I think B is your correct answer. Yes. So by the logic only you can solve this, but still let's draw the entire bending moment diagram. Okay. Wait a moment. Okay. So there is a couple acting here, M, right? Now the reactions at this point and this point will be equal and opposite, and they will be equal to M. Okay, so the moment developed by them will be equal to M. Okay, so if I take moment here, it will be this reaction into L equal to M, so M by L. Now this moment is acting clockwise, so the couple formed by these two reactions should be anti-clockwise. So it will be like this. M by L, M by L. Can you see? These two are forming an anti-clockwise couple in order to balance this. Okay. Now, this is L, this is L. So if I draw the bending moment diagram, what I am going to get? At this point, bending moment is 0. From here to here, bending moment will be straight, right? M by L into L. So here, the bending moment will become M. Right? Then here, if I calculate the bending moment from here to here, bending moment is going to be constant. So it will be like this. This is 0, this is 0, minus M, minus. So this is the bending moment diagram. Yes. So B is the correct answer. Very good, very good. Shall we move on to the next question? Let's go. So this is from GATE Aerospace 2011. Consider a cantilever beam having length L equals to 1 meters. Square cross section, width and depth both are 0.01 meter and Young's modulus 50 gigapascal. The beam is subjected to a transverse load of 1 Newton at the mid-span, means at L by 2 at the center of the cross section. Under the small deformation theory, the transverse deflection of the beam at its free end is. So we need to find deflection at the free end of the cantilever. But the load is not acting at the free end, the load is acting here. So how do you find deflection here? When you have a situation like this, what is the formula of calculating deflection? The load is acting here. What is the load? It is, let's say, P. This distance is L by 2. This distance is L by 2. And this point is A, let's say. This point is B. This point is C. So from here to here, the elastic curve will remain straight. It goes something like this, right? So Y at point A is actually YB plus theta B multiplied by AB, right? Where YB and theta B are the slope and deflection at point B, which you can calculate directly from the formula, right? So let's calculate YA first. So YA is YB plus theta B multiplied by AB. So first we will calculate it in terms of PL and EI. Okay, then we'll put the values. So YB will be equal to what? WL cube by 3 EI. So it will be P into L by 2 whole cube by 3 EI. Theta B will be WL square by 2 EI. And from A to B, length is L by 2. So how much will it be? 5 PL cube by 48 EI in terms of the variable. Now let me put the values here. So the value of P is 1 Newton, length L is 1 meter, Young's modulus is 50 gigapascal, and the width and depth are 0.01 meter. 0.01 meter means 10 mm. Okay. So let's put all the values here. So 1 Newton, length is 1 meter means 1000 mm. 50 gigapascal means 50 into 10 to the power 3, and I will be 10 to the power 4 by 12. So from here, I will get the deflection in mm. .5 mm. Yes. This is the deflection at the free end of the cantilever beam. 2.5 mm. Very good, Deepak. Very good, very good. Chalo, let's move on to the next question. This is from GATE 2010. a thin rectangular plate made of isotropic material which satisfy octahedral or one Mises theory or distortion energy theory has yield strength of 200 megapascal under uniaxial tension. Means SYT is 200 megapascal. As shown in the figure, if it is loaded with uniform tension of 150 megapascal along the x direction, maximum uniform tensile stress that can be applied along the y direction before the plate starts yielding is about. So here sigma x is given as 150 megapascal. You need to find sigma y according to von Mises theory. Yield strength is 200 megapascal, right? So according to von Mises theory, sigma 1 square plus sigma 2 square minus sigma 1 into sigma 2 is equal to SYT by FOS whole square, right? Now here sigma 1 will be sigma x 150 megapascal because there is no tau on these planes. So these two stresses are the principal stresses. So 150 megapascal, I will consider sigma y to be sigma. Okay, both are tensile. See, here they are asking you at which stress the material will fail. So factor of safety will be 1. Yield strength is 200 megapascal, so it will be 200 square. Okay, so from here I will get sigma square minus 150 sigma. 150 square minus 200 square is minus 17500 equal to 0. So you will get two values of sigma. It will be a quadratic equation, right? (227) and minus 77. 227 and minus 77. Now minus 77 cannot be the answer because they are saying that it is a tensile stress. So it should be positive. So 227 megapascal must be the correct answer, right? Yes, very good. A 227 megapascal will be the correct answer because 77 megapascal will be the compressive stress, right? And sigma y is tensile. Okay. Moving on to the next question. This is from GATE 2009. The buckling load for a simply supported column of rectangular cross section of dimensions 1 centimeter by 1.5 centimeter and length 0.5 meter made of steel, Young's modulus 210 gigapascal is approximately. So we need to find the buckling load, critical buckling load. You can apply Euler's theory of buckling. It's a simply supported column, means both ends can be assumed to be hinged, right? Means effective length will be equal to L. So P critical will be equals to pi square EI by L square. Effective length will be equal to L, right? Now, what will be the Young's modulus? 210 gigapascal. So 210 into 10 to the power 3 megapascal. I, so it is 10 by 15. So here we need to put the minimum I, right? So 15 into 10 cube by 12 divided by L square. What is the length? It's 500 mm. So from here I will get P critical in Newton, which can be later converted into kilonewton. (10,363.08 Newton So 10.36 kilonewton. Yes, easy. 10.36 kilonewton means the correct answer is almost A. Yes, very good. 10.36 kilonewton. So the correct answer is A. Moving on to the next question. This was from GATE 2009. Let's see which is next. Okay. The deflection Y of a certain beam of length L and uniform weight per unit length W is given as Y equal to W by 48 EI. Means in terms of X we have the deflection equation. X is the distance from the point of support and EI is a constant. The non-dimensional location X by L where the deflection of the beam is maximum is. We have the equation of deflection in terms of X. We need to find where the deflection will be maximum. You know that the deflection will be maximum where the slope is what? 0, right? The deflection will be maximum where the slope is 0. Usually in case of simply supported beam or overhang beam, it happens. So we will assume, although it is not written here, but we will assume that it's a simply supported or overhang beam. So the slope will be 0 where the deflection will be maximum, right? The deflection Y is maximum at dy by dx equals to 0. Now this W by 48 EI, it's constant, right? So this we don't have to consider. It will become d by dx of 2x to the power 4 minus 3lx cube plus l cube x equal to 0. Yes. Now if I differentiate this equation with respect to x, what I am going to get? 8x cube minus 9lx square plus L cube equal to 0. Yes. Now here we need to find x by L at which the deflection is maximum, right? X by L. So can I put, first we will divide this entire equation by L cube. Okay, so what it will become? 8x by L cube minus 9x by L whole square plus 1 equal to 0. I have divided the entire equation by L cube. Now put x by L equal to any constant. Let me put it A. Okay, what it will become? 8a cube minus 9a square plus 1 equal to 0. Now this is a cubic equation which we need to solve. So we will get 3 different values of A. Okay. So I will directly do this using a calculator. What values are we getting? A is equal to, first of all, minus 0.296 means almost 0.3, then 1, then 0.42. See, x by L cannot be negative, right? It can either be 1 or it can be 0.42. Means x can be equal to L or x can be equal to 0.42 L. If I put x equal to L, what I am going to get here? This will become 2 minus 3 plus 1. So this will become 0, right? So at x equals to 1, y will be 0. Deflection will be 0. It means this must be the value, right? So x by L must be 0.42. You understand my logic? This cannot be the answer because it has to be positive. This you can check. You need to check both these values. So if I put x equals to L, this thing is getting 0. So at x equals to L, y will be 0. So it must be 0.42 L. Yes? Okay. This was a very interesting question. Let's move on to the next question, which is from GATE 2014. There are two designs proposed for a shaft of length L with a torque carrying capacity of T. Design 1 is a solid circular cross section of diameter 30 mm and design 2 is a thin walled circular shaft of average diameter 40 mm. Thickness of the wall in design 2 has to be determined such that the maximum shear stress is same in both designs for the same torque. Ratio of mass of shaft using design 1 to mass of shaft using design 2 is. We need to find the ratio of their masses. How do we do it? One is a solid circular shaft, but other one is a hollow thin walled circular shaft. Okay. Now here first we need to find the thickness of this thin walled circular shaft. So how do we do it? Tau maximum in both cases is equal. Means tau maximum in design number 1 is equal to tau maximum in design number 2. Now in case of solid circular shaft, tau maximum will be 16T by pi d cube. But in case of hollow circular thin walled shaft, what is the formula of tau maximum? If you are from mechanical or civil, you might not know it. But if you are from aerospace, you must have studied this thin walled circular shafts. What will be the tau maximum? T upon 2T into mean area, right? Now here, this T will be cancelled because in both cases torque is same, right? We are applying the same torque. What is the diameter here? 30 mm. In the second case, the thickness is unknown, and what will be the mean area? It will be the area enclosed by this mean line. The diameter of this mean circle will be 40 mm. So it will be pi by 4 into 40 square. So from here I am going to get the value of T. Pi and pi will be cancelled. What are you getting? .11, almost 2.11 mm. Okay. Now we need to find the ratio of their masses, right? Now what is mass? Mass is equal to mass per unit volume, means rho, multiplied by volume, means area into length. So I can say that mass is directly proportional to area because the material is same in both cases, means rho is same. Length is also same in both cases, means L is same. So ratio of mass will be ratio of their area. And what will be the area in first case? It will be pi by 4 d square. In second case, it will be pi dt. It's a hollow thin walled circular cross section, so it will be pi dt. So in first case, the diameter is 30 mm. Pi and pi will be cancelled, so 30 square by 4 divided by, in second case, the mean diameter is 40 and thickness is 2.11. So you will get the ratio of their masses. So how much it is? I am getting 2.6658, 2.67, almost 2.67. Yes, A is the correct answer. Very good, very good. 2.68. So this was from GATE 2014. You need to know this formula in order to find the thickness, tau maximum in case of thin walled circular shafts. T upon 2T into mean area. Yes, very good. Let's move on to the next question. This is from GATE 2015. A slender structure is subjected to 4 different loading cases, 1, 2, 3 and 4. Which pair of cases results in identical stress distribution at section SS located far away from both ends? You must know this theorem called St. Venant's principle, right? According to St. Venant's principle, if you are considering a section very far from the point where the load is applied, it doesn't matter how the load is acting. Okay, as long as the total internal force is same in both cases, it doesn't matter how the load is applied. Okay, so what you need to do, the total internal force must be same. So in case of 1, the internal force will be P, right? In case of 2, 3P by 8 plus 3P by 8 plus P by 8 P by 8. So this will also be P. In case of 3, it will be 0. In case of 4, it will be 0. So I think 1 and 2, right? In case of 3 and 4, the total internal force is 0 at this section. 3P by 8 plus P by 8 and minus 3 by 8 minus P by 8. So it will be cancelled, right? Here also the total internal force is 0 at this section. But in these two cases, total internal force is same, P. So it was very easy. Moving on to the next question. This is from GATE 2020. Which one of the following conditions needs to be satisfied for phi equal to ax to the power 4 plus by to the power 4 plus 𝐂𝐻𝐬𝐿 to be considered as an Airy's stress function? Now this is also another topic which is only relevant for aerospace. So other branch students might not know this. This is from GATE Aerospace. Airy's stress function, right? It's a function which is used to find stresses, right? So if it's Airy's stress function, it has to satisfy what? Which equation? Compatibility equation, right? Dou 4 phi by dou x to the power 4, right? Plus dou to the power plus dou to the power 5 by dou y to the power 4 plus 2 dou square phi, dou to the power 4 phi by dou square x dou square y equal to 0. Yes, it has to satisfy this. So put it and find out which equation is satisfying this. So if I differentiate this equation with respect to x 4 times, this and this will be 0. This will be how much? 24a, right? This will be 24a. Then if I differentiate with respect to y 4 times, this and this will become 0. This will become 24b. And if I differentiate this x and y 2 times, what I am going to get? This will become 0, na? So a plus b equal to 0. Are you getting this? A plus b equal to 0. Yes. Okay. Moving on to the next question. This is from GATE 2013. A simply supported beam with overhang is loaded by uniformly distributed load of intensity Q as shown in figure. Bending moment at the midpoint of AB is. We need to find bending moment at a particular section. We need to also tell what is the nature of the bending moment, whether it is sagging moment or hogging moment. Okay. So how do you solve this? First you need to find the reactions, right? So it's an overhang beam. Which is subjected to uniformly distributed load Q. There will be one reaction here and one reaction here. This is point A, this is point B. Let's call this point as the center C. Okay. L by 2, L by 2, L by 2. So first we need to find the reaction. So where should we find the reaction? So let's take moment at point B. So if I take moment at point B, the moment of RA will be RA into L minus the load of UDL will be Q into L plus L by 2. Okay. And distance will be 0.75 L, right? Here it will be 0.75 L at the center. So from here to here, what will be the distance? This is L and this is 0.75 L. So this will be 0.25 L or L by 4. So what will be the value of RA? QL by 8. This is the value of RA. Okay. Now we need to find the bending moment at point C. So the bending moment of RA will be PQL by 8 multiplied by L by 2 minus moment due to UDL will be Q into L by 2. This will be the load multiplied by distance from center L by 4. So 3 by 16 minus 1 by 8. 3 by 16 minus 2 by 16 will be 1 by 16. So QL square by 16, and according to my sign convention it is positive, means it is sagging. I have considered sagging moment to be positive and I am getting a positive answer, means it is sagging. So QL square by 16 sagging. So A is the correct answer. Yes. So the max bending moment at the center midpoint of AB is QL square by 16. Okay. Sagging. Moving on to the next question. Now this is from GATE 2017. For the state of plane stress shown in figure, minimum principal stress is -7 megapascal. Normal stress sigma x in megapascal is equal to. So it is subjected to biaxial state of stress. Sigma x, sigma y, both are tensile. Tau is 56. Sigma x is not known. Minimum principal stress is -7 megapascal. Okay. So what are the principal stresses in case of biaxial state of stress? Sigma 1 2 is equal to sigma x plus sigma y by 2 plus minus root over sigma x minus sigma y by 2 whole square plus tau xy square. Now you can see that both sigma x and sigma y are tensile. So if that's the case, you will only get negative principal stress if you take negative value, negative sign here, right? If sigma x and sigma y both are positive, then here you will get only negative value if you take this negative sign. So -7 will be equal to sigma x is unknown, sigma y is plus 21 minus root over sigma x minus 21 by 2 whole square plus tau xy is 56. So if you solve this, you are going to get the value of sigma x, right? Now I have a better way of solving this. Okay, how? You must know these two equations, sigma 1 plus sigma 2 equal to sigma x plus sigma y, and sigma 1 into sigma 2 is equal to sigma x into sigma y minus tau xy square. If you use these equations, it will be way better than solving this equation. Let me show you how. See, sigma 2 is, let's say, minus 7, sigma 1 is unknown. So sigma 1 minus 7 equal to sigma x plus 21. Okay, so from here I will get the value of sigma 1, which will be sigma x plus 28. Okay, got it. Now the second equation, sigma 1 into sigma 2 means sigma x plus 28 into sigma 2, which is minus 7, equal to sigma x into 21 minus tau xy square, which is 56. So from here you will get a simple equation in terms of sigma x, right? Sigma x plus 28 equal to, this will become minus 3 sigma x plus 56 square by 7. How much it is? 448. So 4 sigma x equal to 448 minus 28, 420. So sigma x will be equal to 420 by 4, 105 megapascal. See how easy it was to solve using these two equations, right? 105 megapascal. You can solve this equation also, but it will take a lot more time compared to this. Okay, so 105 megapascal is the correct answer. Okay, chalo. Moving on to the next question. The components of stress in a body under plane stress condition in the absence of body forces is given by sigma xx equals to ax square, sigma yy equals to 12x square minus 6y square, and tau xy or sigma xy is 12xy. The coefficients of A such that the body is under equilibrium is. Now this is another question which will be solved only by aerospace students, because this equilibrium condition is also studied by aerospace students only, right? What is the equilibrium condition? There are two equations, right? Dou sigma x by dou x plus dou tau xy by dou y equal to 0. One equation is this, dou sigma x by dou x plus dou tau xy by dou y equal to 0. And another equation is dou sigma y by dou y plus dou tau xy by dou x equal to 0. So these two equations must be satisfied, right? So dou sigma x by dou x. So here sigma x is ax square and tau xy is 12xy. So if you differentiate this with respect to x partially, what you are going to get? 2ax. If you differentiate this with respect to y partially, you will get 12x. So from here a will be equal to minus 6, na? Are you getting minus 6? Are you getting this? Minus 6. Yes? Very good. Let's move on to, acha, we don't need to use this second equation. Let's move on to the next question. Consider a beam in bending with solid circular cross section of 1 mm square, which is to be subjected to a transverse shear force of 1 Newton. The shear stress at the center of the cross section is. In case of solid circular cross section, shear stress is maximum at the center, right? And the equation of shear stress, tau maximum, will be 4 by 3 times of tau average, right? In case of rectangular cross section, it is 3 by 2 times of tau average. In case of circular section, it will be 4 by 3 times of tau average. In both cases, tau maximum is at the center for rectangle as well as for circle. Now, what is tau average? It is force upon area. So, shear force is 1 Newton and area is 1 mm square, right? So, what is tau maximum? It is very easy, right? Question, 4 by 3 or 1.33 Newton per mm square or megapascal. 1.33 is the correct answer. The force is given 1 Newton, the area is given 1 mm square. So force upon area is 1. So 4 by 3 means 1.33 megapascal, right? Yes. Moving on to the next question. Now this is from GATE 2011. A simply supported slender column of square section has to be designed such that it buckles at the same instant as it yields. Length of the column is given to be 1.57 meter and it is made of a material whose Young's modulus is 200 gigapascal and yield stress is 240 megapascal. Width of the column should be. Here the buckling load and the yielding load both must be same. Okay. Buckling load and yielding load. Yielding load means yield strength into area, right? So you need to equate both P critical and P yielding. P critical must be P yielding. Okay. Now what is P critical? It is a simply supported column, so pi square EI by L square. LE will be equal to L. And this will be sigma y into area. Okay. So pi square E. What is E? 240 megapascal. I. So I will be, it's a square cross section of dimension D. So D to the power 4 by 12 divided by length. Length is 1.57 meter. So 1570 mm. This will be equal to yield strength is 240 megapascal. Oh, so sorry. Young's modulus is 200 gigapascal. So it will be 200 into 10 to the power 3. This is 240 megapascal and area will be D square, right? So from here you will get the value of D. What is the answer? $59.97, almost 60 mm. Are you getting this? D, almost 60 mm. Please tell me you are getting this. The value of D, width D, is almost 60 mm. Okay. Moving on to the next question. This is from GATE 2019. A thin walled tube with the cross section shown in figure is subjected to a torque of 1 kilonewton meter. The walls have uniform thickness of 1 mm and shear modulus 26 gigapascal. Assume the curved portion is semicircular. Shear stress in the wall is. Now this is again related to thin walled shafts, non-circular, circular shaft subjected to torsion, right? Thin walled tubes. In case of thin walled tubes, what is the equation of tau? Tau maximum. Tau maximum is T upon 2 into T into mean area, right? So what is the torque here? It is 1 kilonewton meter. Convert it in Newton mm. So 1 into 10 to the power 6. What is the thickness? Thickness is 1 mm and it is constant. What is the mean area? So here this line is given the center line, mean line. Okay. So we need to calculate this total area. We can divide it into a triangle plus a semicircle. So the triangle is half into base into height. So half into, what is the base? 0.5 meter means 500 mm and height is 50 mm plus semicircle pi r square by 2. Okay, so sorry, this radius is 50 mm, so height will be 100 mm, na? Plus pi r square by 2. So pi into 50 square by 2. This will be tau maximum. Okay, what is this AM? Mean area. Area enclosed by this center line, mean line. Okay. $17.28 megapascal. Are you getting this? 17.28 megapascal. Yes. This is the maximum shear stress in the cross section, right? Now this is from GATE 2011. A body undergoes deformation under plane strain condition when subjected to the following stresses: sigma x equals to 450 megapascal, sigma y is 450 megapascal again, tau xy is 75 megapascal, tau xz and yz are 0. What are the remaining component of stresses and strains? Assume the material to be isotropic and linear elastic with Young's modulus E is equal to 200 gigapascal and Poisson's ratio is 1 by 3. Okay. So here sigma x, sigma y, tau xy are given. The rest of the stresses are 0. Okay. Tau xz, yz are 0, not rest of the stresses. Plane strain condition is given. Okay. In case of plane strain, epsilon z is 0, right? In case of plane strain condition, epsilon z is 0. So by putting epsilon z equal to 0, we can find sigma z, right? So epsilon z, which is equal to sigma z by E minus nu sigma x by E minus nu sigma y by E equal to 0. Okay. So from here, sigma z will be nu into sigma x plus sigma y. And what is nu? Nu is 1 by 3. Sigma x and sigma y both are 450. So from here, sigma z will be 300 megapascal. Okay. So we know that A and D cannot be the correct answers. B and C, either B or C is the correct answer, right? Now in both cases, you can clearly see that epsilon x is different. So if you calculate epsilon x, you will know which one is the correct answer. So epsilon x will be sigma x by E minus nu sigma y by E minus nu sigma z by E, right? So 1 by E is common and E is 200 gigapascal. So 200 into 10 to the power 3. Sigma x is 450. minus 1 by 3 into 450 minus 1 by 3 into 300. So this will give you epsilon x. So 450 minus 150 minus 100 by 200 into 10 to the power 3. It is 1 into 10 to the power minus 3, or you can say 0.001. So which one is the correct answer? B is the correct answer. Sigma z is 300 and epsilon xx is 0.0001. Epsilon y will also be same. Why? Because if sigma x and sigma y are equal, epsilon x and epsilon y are also equal. So epsilon y will also be same. Okay. Gamma xy you can calculate using tau xy, and g you can calculate using E and U, but we don't need to do that, right? It should be compressive. Why it should be compressive? Is it written anywhere that it is compressive? Sigma x, sigma y both are tensile. Where is it written? Okay, let's move on to the next question. This is from GATE 2011. Again, a question from Airy's stress function. Which of the following Airy's stress function could satisfy the given boundary conditions, assuming constant values of sigma xx equals to p, sigma yy equals to q, and tau xy is equal to r along the boundary? Okay. So another question from Airy's stress function, and let me remind all the students of mechanical and civil that you guys don't study Airy's stress function, so you might not be familiar with this particular topic. Okay. So what is Airy's stress function? Actually, it's a function, a continuous function which can be used for calculating the state of stress at a point, right? Phi is equal to how much? Acha. Let's say phi is equal to ax square plus by square plus cxy, right? Plus cxy. So this is the Airy's stress function. Now we need to find sigma xx equals to p. Okay, so we need to find the values of a, b and c. So how do we do it? Sigma x is equal to what? Dou square phi by dou x square. Yes or no? No, it's dou y square, na? Dou square phi by dou y square. So if you put it here, this will be equal to what? B, right? And it is equal to p. Sorry, dou square y by dou y square, na? So it will be 2b, which will be equal to p. So b will be equal to p by 2. Now sigma y is dou square phi by dou x square. So if I put it here, this will become 2a. And what is sigma y? It is equal to q. So from here, a is equal to q by 2. Now we need to find the value of r, na? And tau xy is minus dou square phi by dou x into dou y. So if I differentiate this equation one time x, one with respect to x, another time with respect to y, these two will be 0. This will become minus c, and tau xy is equal to r. So c will be equal to minus r. So your phi will become how much? A is q by 2. So q by 2x square plus p by 2 y square minus rxy, right? Qx square by 2 plus py square by 2 minus rxy. C is the correct answer. Yes. Chalo. Very good. Let's move on to the next question. and this is from GATE 2013. In the steel structure shown in figure, all members have a circular cross section of radius 10 mm. Column BD is pinned at B and D. The support at A is hinged. The minimum value of load P at which column BD may buckle is approximately. So we need to find the value of P at which column BD is going to buckle. Now, if you apply a force here, what will be the reaction here? If I consider this AC, yes, this is point A, point B, point C, right? This is P. Let me call it RB. Let me call it RA. What are the distances? 1 meter, 1 meter. So if I take moment at A, then RB into 1 minus P into 2 will be 0. So RB will be 2P. So this column BD is subjected to a force 2P. Okay. And the critical load of buckling will be equal to what? Pi square EI by L square, because both ends are hinged. So LE will be equal to L. Okay. So what will be P critical here? It will be 2P, because BD is subjected to the force 2P. This will be equal to pi square E. Young's modulus is how much? 200 gigapascal. So 200 in 10 to the power 3 megapascal I. So it's a circular cross section of radius 10 mm means diameter 20 mm. So pi by 64 into 20 to the power 4 divided by L. Length is 2 meters. So 2000 mm. So from here you will get the value of P. (1937.89 Newton) in terms of the unit is not given, na? The unit must have been mentioned, not mentioned. So let me write it in Newton only. 1937.89 Newton. Is this session helpful for mechanical? Yes, of course. This question is also relevant for mechanical engineering students. Yes. Let's move on to the next question. Now this is from GATE 2020. Aerospace thin walled beam of constant thickness is subjected to a torque of 3.2 kilonewton meter. Shear modulus is 25 gigapascal. What is the angle of twist per unit length? So how do you calculate the angle of twist in case of a closed thin walled tube subjected to torque T? What is the equation of, it's given in question, where it is given, minimum load P at which column BD, acha, in Newton it is written, na? So sorry. So here we need to find the angle of twist, right? Theta, and theta is given by TL by 4A square G. Integration ds by T, right? And if thickness is constant, then this will become total length by thickness. So put the values here. What is torque? Torque is 3.2 kilonewton meter. Those of you who are not from aerospace, please ignore this question because you might not know this concept. Okay. So 3.2 into 10 to the power 6. Length. What is the length? Acha, per unit length. So 1000 mm I will put. 1 meter means 1000 mm, na? Mean area. So what is the mean area? 400 by 100, na? So 400 by 100 square into G. What is the shear modulus? 25 gigapascal. So 25 into 10 to the power 3 megapascal. What is the total mean length? So 400, 400, 800, 100, 100, 1000 divided by T, which is 2 mm. So what is theta in radian per meter? Point 0.01 radian per meter. Is this the answer? 0.01. Are you getting this? 0.01 radian per meter. Chalo. Moving on to the next question. This is from GATE 2014. It is desired to measure Young's modulus and Poisson's ratio for a given homogeneous isotropic material. Bar of length 20 cm and square section is subjected to tensile load of 40 kN. Under this load, length increases to 20.1 cm. Means 0.1 cm is the change in length. Cross section reduces to 9.98 by 9.98 mm. Young's modulus and Poisson's ratio of the material are. So here we need to find the Young's modulus and Poisson's ratio, right? So how do we find the Young's modulus? Delta L is equal to PL by AE. So E will be equal to PL by delta L into A. So what is the load P? 40 kilonewton. What is the length? Length is 20 centimeter, na? So 200 mm. Change in length is 0.1 centimeter means 1 mm, and area, initial area is 10 by 10. This should be the original area, okay? So 40 into 10 to the power 3 into 200 by 10 into 10. So 80,000 megapascal means 80 gigapascal. Now we need to find the Poisson's ratio. How do we find Poisson's ratio? Minus of epsilon lateral by epsilon longitudinal, right? So minus of delta D by D, where D is the lateral dimension, divided by delta L by L. So what is delta D? So delta D is, see, this minus and this minus will be cancelled. So I can just put it plus, because delta D is negative, na? So from 10 mm to 9.98 mm. So 10 minus 9.98, 0.02 mm. So lateral dimension is decreased by 0.02 divided by 10 divided by length is increased from 20 centimeter to 20.1 centimeter. So 1 by 200. So this will give you the Poisson's ratio. So how much is the Poisson's ratio? 0.02 into 200 by 10. 0.4 is the Poisson's ratio. So Young's modulus is 80 gigapascal and Poisson's ratio is 0.4. It will not be negative, it will be positive, right? Yes. So A is the correct answer. Moving on to the next question. This is from GATE 2014. It must be 2 marks. Which one of the following objects with inclined face at 45 degree subjected to given stresses are in static equilibrium? you need to find which of these are subjected to static equilibrium. Equilibrium equations must be satisfied, means summation of fx and summation of fy must be 0. Okay, but you must know one thing. See, usually people make mistake that they directly consider these to be forces. These are not forces, these are stresses, they are tensor quantities. They have to be converted into vector quantities, right? So here you can see this angle is 45, na? So if let's say this is L, this is L, so what will be this? Root 2L, right? So this 35 megapascal and 5 megapascal, these are stresses, they have to be converted into force. So let me check any one of these. If I check B, what I will get? Here it is 30 megapascal. Here it is 40 megapascal. This is what? 35 megapascal. And this is what? 5 megapascal. So let's see whether it is in equilibrium or not. Okay. So if I resolve this 35 megapascal, what I will get? 35 into area. Thickness is, let's say, 1. 35 into root 2L cos 45, na? And this will be 5 into root 2L sin 45. So summation of fx will be 35 into root 2L cos 45 minus 5 root 2L cos 45 minus 30. So is it 0? Summation of fx. So cos 45 is 1 by root 2. So 35L minus 5L minus 30L. So summation of fx is 0, right? Yes. Jackpot. The first option that we have checked is the correct one. So B is the correct answer. Yes, because all the other options are completely different from B. So none of them will give you the right answer. So B is the only correct option. Yes. Okay. So do you understand? You have to convert the stress into force, and force will be stress into area. Now here thickness is, let's say, unit. Okay, 1 unit. So area will be, this area will be root 2L into 1. This area will be L into 1. This area will be L into 1. So what I did, I calculated the net force in x direction. 35 megapascal, convert it into force. So 35 into root 2L. Cos component, cos 45. Okay. Similarly, 5 megapascal, 5 into root 2L into again cos 45. And this will be 30 into L. Yes. So B is the correct answer because the net force in x direction is 0. Okay. Moving on to the next question. Now this is from GATE 2014. Consider the plane strain field given by epsilon xx equals to 10xy square, epsilon yy equals to minus 5x square y, and gamma xy is equals to axy 2x minus y, where a is constant, gamma xy is engineering shear strain. Value of constant a for strain field to be compatible. What is the compatibility equation in terms of strain? Rho square epsilon x by dou I square plus dou square epsilon y by dou x square equals to dou to the power 4 gamma xy by dou square gamma xy by dou x dou y. This is the strain compatibility equation, na? If it was MSQ, then we have to check all. Yes, but it is not an MSQ, and you can see that all the other options are completely different. Okay, chalo. So here put the equation. So dou square epsilon x by dou y square. So if I differentiate this with respect to y 2 times, it will be 20x, right? Plus dou square epsilon y by dou x square. So this will become minus 10y. This will be equals to dou square epsilon xy by dou x dou y. Gamma xy, sorry, by dou x dou y. So if I differentiate this with respect to x one time and with respect to y one time, what I will get? This is what? So let's calculate this, na? Dou gamma xy by dou x. This will be, first of all, what is gamma xy? A into 2x square y minus xy square, right? So if I differentiate this with respect to x one time, so it will be 4xy minus y square. And if I differentiate this again with respect to y one time, what I will get? 4x minus 2y. Okay, now we have this. A into 4x minus 2y. Okay, so if I take y 5 from here, 4x minus 2y, to a 4x minus 2y, 4x minus 2y, 4x minus 2y will be gone. A will be equal to 5. Are you getting this? A will be equal to 5. This strain compatibility equation is also a concept which is only taught to GATE Aerospace. So if you are from another branch, you might not know this equation. Okay, this is strain compatibility equation. Yes. Moving on to the next question. Now this is from GATE 2014. A 1.8 meter long steel beam of rectangular cross section is simply supported with a length of 1.2 meter between the supports and overhang of 0.3 meter on either side. Young's modulus of the material of beam is 200 gigapascal. For a 50 Newton load applied at the center of the beam, magnitude of the slope at the tip S is. You can see this is an overhang beam, but the good thing is there is no load acting on the overhang. So if there is no load acting on the overhang, the elastic curve will remain straight, right? So this is going to be the elastic curve. So from P to Q, the slope will be constant. From R to S, the slope will be constant. So whatever slope you will get at point R, you will get the same slope at S. And you know the slope for simply supported beam, right? At point R, theta S will be equal to theta R, which will be WL square by 16 EI. Simply calculate this. So W is 50. Length, we will consider this simply supported beam, means 1200 mm divided by 16 EI. What is E? 200 gigapascal. And I, so it's a rectangular cross section, BH cube by 12. So 10 into 6 cube by 12. This will give you slope S. So it is 0.125 radians, right? This is the slope at the tip from R to S. The slope will be same. From P to Q, the slope will be same, 0.125 radians. Okay. Chalo. Moving on to the next question. A structural member of rectangular cross section 10 mm by 6 mm and length 1 meter is made of steel, Young's modulus 200 gigapascal and alpha 12 into 10 to the power minus 6 per degree centigrade. It is rigidly fixed at both ends and then subjected to gradual increase in temperature. Ignoring the three-dimensional effects, structural member will buckle if the temperature is increased by delta T, which is. So we need to find the delta T at which this column will buckle. The column will buckle when the force P developed due to temperature change will become equal to P critical, right? P due to delta T will become equal to P critical. What will be P due to delta T? It will be sigma due to delta T into area. Sigma due to delta T will be E alpha delta T into area. So it will be A E alpha delta T. And what is P critical? Pi square EI by LE square. And as both the ends are fixed, LE will be equal to what? 2L, right? When both, LE will be equal to L by 2, right? When both ends are hinged, LE is equal to L. When both ends are fixed, LE will be equal to L by 2. So here E will be cancelled. Area is 10 by 6. Alpha is 12 into 10 to the power minus 6. Delta T is unknown. I will be BH cube by 12. So 10 into 6 cube by 12. You need to put minimum I. L by 2. So 1 meter means 500 mm. L by 2 means 500 mm. So from here, we'll get the value of delta T. .87 degrees centigrade. This is the change in temperature that is required for the column to buckle. 9.87 means C is the correct answer, right? This is from GATE 2014. Okay. Another question from GATE 2014 must be 2 marks. There is no question of 3 marks. So sorry. A gas cylinder, closed thin-walled cylindrical pressure vessel of diameter 30 cm and wall thickness 1 mm is subjected to design maximum internal pressure. Subjected to a design maximum, withstand maximum pressure of 0.5 megapascal. Material used for manufacturing this has a failure stress of 260 megapascal. Assuming von Mises failure criteria, factor of safety for this cylinder is. So according to von Mises stress criteria, sigma 1 square plus sigma 2 square minus sigma 1 sigma 2 equal to SYT by FOS square. What will be sigma 1? So sigma 1 will be equal to sigma L PD by 4T. Okay. Or you can say sigma C PD by 2T. It's your choice. So 0.5 megapascal. Diameter is much? 30 centimeter means 300 mm. Thickness is how much? 1 mm. So 150 by 4. 37.5 megapascal is the longitudinal stress. Sigma 2, second principal stress will be sigma C, PD by 2T, means 2 times of this. No need to calculate again, just multiply 2 here, so 75 megapascal. So these two are the principal stresses, right? Now, according to von Mises theory, sigma 1 square plus sigma 2 square minus sigma 1 sigma 2 equal to SYT by FOS whole square. So in this equation, we have sigma 1, sigma 2 and we have SYT 260, right? We need to find factor of safety. So 37.5 square plus 75 square minus 37.5 into 75 equals to 260 by FOS whole square. So from here, we'll get FOS. 2.62 is the factor of safety. 0.62 means almost 2.8. A. You're getting this? $2.62. Yes. Almost 2.8 is A. This we have already solved, na? So sorry, it is repeated again. A cube made of linear elastic isotropic material is subjected to uniform hydrostatic pressure of 100 Newton per mm square. It must be Newton. 100 Newton per mm square. Under this load, volume shrinks by 0.05%. Young's modulus of the material E is 300 gigapascal. Poisson's ratio of the material is. We need to find the Poisson's ratio. This is from GATE 2015. So what is the volumetric strain epsilon V? Epsilon V is delta V by V, which is 1 minus 2 nu by E sigma x plus sigma y plus sigma z. Okay. And it is 0.05% means 0.05 into 100. Percentage strain means 100 times of strain. Okay. So if epsilon V is 0.05% means 0.05 into 100. So it will be 0.05 into 100, na? Or 0.05 divided by 100, na? Sorry. Divided by E, 300 gigapascal, 300 into 10 to the power 3. Sigma x, sigma y, sigma z all will be same, 100. This will become 300, na? From here, what is the value of nu? Point 0.25. 0.25 Poisson's ratio. This is the Poisson's ratio, 0.25. Another question from GATE 2010. Following stress state is proposed for a two-dimensional problem with no boundary forces. Sigma xx is equals to 3x square y plus 4y square. Sigma yy is equal to y cube plus 14xy. Tau xy is minus 3xy square minus 7x square. Then it satisfy equilibrium equations but not compatibility equation, compatibility equation but not equilibrium equation, neither equilibrium nor compatibility, or both equilibrium and compatibility. So first you need to check the equilibrium equations, then you need to check the compatibility equation. What is the equilibrium equation? First, let's check equilibrium equation. Okay. What is the equilibrium equation? Del dou sigma x by dou x plus dou tau xy by dou y is equal to 0. Let's check. Dou sigma x by dou x. So this will become 6xy plus dou tau xy by dou y. So this will be minus 6xy. This is 0, so it is satisfied. Then dou sigma y by dou y plus dou tau xy by dou x. So dou sigma y by dou y will become 3y square plus 14x. Then plus dou tau xy by dou x. So this will become minus 3y square minus 14x. This is 0. So equilibrium equations are satisfied. Na? Equilibrium equations, both equations are satisfied. Now compatibility equation. So earlier we have seen strain compatibility equation. What is the compatibility equation in terms of stress? Dou square by dou x square by dou square by dou y square sigma x plus sigma y equal to 0. You can write it, right? Compatibility equation. So dou square by dou x square plus dou square by dou y square. What is sigma x? Sigma x is 3x square y plus 4y square. And what is sigma y? Sigma y is y cube plus 14xy. Equal to 0. Okay. So if I differentiate this entire equation with respect to x 2 times, so this will be 6xy, 6y, 0, 0, 0. Okay. And if I differentiate this entire equation with respect to y 2 times, this and this will be 0. This will be 8 plus 6y, which is not equal to 0, right? This is not satisfied. Huh? This is not satisfied. So compatibility, equilibrium equations are satisfied, but compatibility equations are not satisfied. A is the correct answer. Yes. Okay. Moving on to the next question. This is from GATE 2015. A massless cantilever beam PQ has a solid square cross section 10 mm by 10 mm. The beam is subjected to a load W through a rigid massless link at point Q. If Young's modulus is 200 GPa, deflection at point Q is. We need to find deflection at point Q, and in order to do that, what we can do, we can remove this rigid link. Okay, rigid massless link. So if I remove this rigid massless link and if I transfer the load at point Q, I am going to get 100 Newton will be the force, and we are also going to get a couple, clockwise couple, 100 into 5, 500 Newton mm. This is the length, 300 mm. This is point Q. So we need to find the deflection at Q, na? So how can you find it? Due to point load, it will be WL³ by 3 EI, and due to couple, it will be ML square by 2 EI. Okay. So E and I are common. So can we take it out? E and I. So E is 200 gigapascal and I will be 10 to the power 4 by 12. 200 into 10 to the power 3. I will be 10 to the power 4 by 12. So EI I have taken out. WL³ by 3. So 100 into 300 cube by 3 plus ml square by 2. 500 into 300 square by 2. So from here you will get the deflection in mm. .535 mm. I am getting this 5.535 mm. This is the deflection at the end Q. 5.535 mm. Yes. Okay. Moving on to the next question. This is again from GATE 2015. A 200 mm simply supported column has rectangular cross section, Young's modulus, corresponding factor of safety. Maximum load the column can support in compression is. See, P critical will be pi square EI by L square. Okay. So pi square into 200 into 10 to the power 3. I will be minimum I. So 10 into 5 cube by 12, BH cube by 12 divided by L square, simply supported. So LE will be equal to L, so 200 square. So from here you are going to get the P critical, but they are not asking you to find P critical, right? They are asking you to find the safe load that you can apply, maximum safe load. So 5140.42 Newton, but the safe load will be P critical by factor of safety. Okay. So factor of safety is 2.5. So 5140.42 divided by 2.5. So what is the safe load? 2056.17 Newton. So this is the maximum load that you can apply without buckling. Okay. A bar made of linear elastic isotropic material is fixed at one end, subjected to axial force of 1 kN at the other end. Cross sectional area is 100 mm square, length is 100 mm, Young's modulus is given. Strain energy stored in the bar is how much? Newton mm. What is the formula of strain energy? U in case of axial load, P square L by 2AE. Okay, just put all the values here. P is 1 kilonewton, means 1000 Newton. Length is 100 mm. Cross sectional area is 100 mm square. And Young's modulus is 1 into 10 to the power 5. So from here you will get strain energy in Newton mm. Five Newton mm. Yes, 5 Newton mm. Very good, yeah. 5 Newton mm. Okay. Now this is from GATE 2016. A cantilever beam spring system is shown in figure. So we have a beam which is connected to a spring at the end. It is subjected to, Young's modulus is given and geometry is such that moment of inertia is 100 mm to the power 4, length is also given. EIL, all are given. It is supported by a spring of stiffness. Stiffness is also given. It is subjected to a load P equal to 100 Newton at point B. Deflection at point B due to the load P is. We need to first find the spring force, right? If I remove the spring from the beam, it will look like this. It is subjected to a force P here. Then due to spring, there will be some reaction force here. Let's say this is R. Okay. So this is point B. We need to first find this R, 100 Newton. So how do you find R? Compatibility equation. Deflection of B will be equal to deflection of spring. What will be deflection of B? It will be equal to 100 L cube by 3 EI minus R L cube by 3 EI equal to deflection of spring will be R by K. So in this equation, put all the values and you will get the value of R. Once you get the value of R, R by K will give you the deflection of B, right? So 100 into, what is the length? 100 mm. 100 cube divided by 3 into E is 1 into 10 to the power 5 and I is 100. What is the stiffness in Newton per mm? 30. So by solving this, you will get the value of R. R is 50 Newton. Okay. That's it. Now we can find YB using R by K. YB is Y of spring, which is R by K. So R is 50 and K is 30. So 5 by 3 means 1.67 mm. This is the deflection of the point B or deflection of spring also. Same will be the deflection of spring also. Okay, 1.67 mm. Okay. Moving on to the next question. Now this is from GATE 2017. A batch of aluminum alloy yields in uniaxial tension at the stress of 330 megapascal. If this material is subjected to following state of stress, sigma x, sigma y and tau xy in terms of x is given. Value of x that would result in yielding according to von Mises failure criteria is. So first we need to find sigma 1 and sigma 2 in terms of x. Okay. Sigma 1 2 is equal to sigma x plus sigma y by 2. plus minus root over sigma x minus sigma y by 2 whole square plus tau xy square. So sigma x is 140, sigma y is minus 70. So 140 minus 70 by 2 plus minus root over 140 plus 70 by 2 whole square plus x square. So this will become 35 plus minus root over 210 by 2 is 105 plus x square. It will become very complicated, na? I have another idea which we can use. Instead of doing this, we can do this. According to von Mises criteria, tau maximum is equal to SYT by root 2, right? Yes or no? Tau maximum is equal to SYT by root 2. What will be tau maximum? It will be root over sigma x minus sigma y by 2 whole square plus tau xy square. Okay, so this will become root over 140 plus 70 by 2 whole square plus x square. This will be equal to SYT by root 2. What is SYT? 330 divided by root 2. Okay, so from here you will get the value of x. I am getting 208.39. You are getting this 208.39 megapascal. Oh, SYT by root 2 or root 2 na? Point 0.57 times or 1 by root 2 times 57, sorry, 0.577, written it. Not root 2, it is root 3. So sorry, my equation was a bit off. Yt is how much? 330 by root 3. It's not root 2, it's root 3. Okay. 330 square by 3 plus 105 square. Answer 158.9. Now this is correct. 158.98 megapascal. Now it is correct. So this is the relation between tau maximum and yield strength according to von Mises criteria. Okay. Hello. Moving on to the next question. This is from GATE 2017. an aircraft wing is idealized as a cantilever beam of constant width and length L with a tip mass of weight W and has a uniformly distributed load of Q0. Flexural rigidity is EI and Q0 L is 10 W. Upward deflection of the tip of the aircraft wing under the given loading can be expressed as delta equals to kWL3 by EI, where value of K is. So it is subjected to UDL plus point load, na? It's a cantilever beam which is subjected to a UDL and a point load, right? The point load is acting downward and UDL is acting upward. Point load is W and UDL is Q0. UDL is Q0. Q0 is 10 W by L. Okay. Now, the tip deflection is kWL3 by EI. Let's say this is A. Upward deflection is positive. Okay. Here they have given this as upward deflection kWL3 by EI. Okay. So YA will be equal to how much? Q0 L to the power 4 by 8 EI minus WL3 by 3 EI. And this is kWL3 by EI. Okay. Now Q0 is 10 W by L. So it will become 10 WL3 by 8 EI minus WL3 by 3 EI. So 10 by 8 minus 3, 1 by 3. 11 by 12. So K is 11 by 12, which is 0.9167 or 0.92. Are you getting this? 0.92. The two-dimensional state of stress in a body is described by Airy stress function. Airy stress function will satisfy equilibrium and compatibility requirements if and only if the value of the constant E is. So here we have Airy stress function phi, which is given in terms of xy, and there is a constant E. We need to find the value of E that the equilibrium equation and compatibility equation is satisfied, right? So how do you solve this? Equilibrium equation and compatibility equation both will be satisfied when this equation is satisfied. This equation, biharmonic equation, is satisfied, then both equilibrium, oh, so have I written? Biharmonic equation is satisfied, then both equilibrium and compatibility equations are automatically satisfied. Na? So if I differentiate this entire equation with respect to x 4 times, then this 0, this will be how much? 10, right? The first value will be 10, na? Then if the entire equation is differentiated with respect to y 4 times, then this all will be gone. It will be how much? 2e. Then if this equation is differentiated with respect to x 2 times and y 2 times, this will be 0, this will be 0, will be 0, this will be, you will get this 6, 12. 2e will be equal to minus 22, e will be equal to minus 11. Are you getting this? Minus 11. Yes. This was from GATE 2016 based on Airy's stress function, which only aerospace engineers might. Other branch students, please ignore this question. Okay. Chalo. GATE 2019. Thin plate with Young's modulus E equal to 210 gigapascal. Poisson's ratio 0.3 is loaded as shown in figure. Change in length along y direction. Sigma x, sigma y both are given. So epsilon y will be equal to del y by y. It will be sigma y by E minus nu sigma x by E. Sigma z is 0, right? So delta y divided by y. Initial y is 200. 1 by E. E is 210 gigapascal. So 210 into 10 to the power 3. Sigma y is 240, sigma x is 100 and nu is 0.3. From here you will get delta y. How much is delta y? 210 will be cancelled. 200 divided by 1000. 0.2 mm. Na? 0.2 mm. Okay. Next is this for the state of stress. Shown in figure, the normal stress sigma n on a plane inclined at 45 degree to x-axis. So this is the question related to stress on oblique plane. Na? Simple question, sigma n you need to find. Na? So sigma at any angle theta is sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. This equation is slightly different in different books because of sign convention. If you take a different sign convention, you'll get a different equation, right? The signs might change. Terms will remain same, signs might change. So sigma x is 200, sigma y is 100. Tau xy according to my sign convention is positive. So sigma x 100, 200, sigma y 100, tau xy is also 100. So 200 plus 100 by 2 plus 200 minus 100 by 2 cos theta. We consider the theta from vertical anti-clockwise positive. So this is cos 90 plus 100 sin 90. Cos 90 is 0, sin 90 is 1. So 300 by 2, 150 plus 100, 250. Yes, 250 megapascal. This is from GATE 2019. For a 1 meter long simply supported beam with concentrated vertical load of 200 Newton, and concentrated bending moment of 100 Newton meter at the center, the correct bending moment diagram is. We need to find the bending moment diagram. Okay. First of all, we need to find the reactions. Newton meter is 200 ton. So what will be the reaction? This will be 200 and this will be 0. Okay. But let me calculate it for you. P, this is Q, this is R, 0.5 meter, 0.5 meter. Okay. So if I take moment at point R, moment of reaction Rp will be Rp into 1. Moment of this couple will be negative minus 100. Moment of this will be 200 into 0.5. What is Rp? Rp will be equal to 0. Rp will be 0. Okay, no, it will be also minus. So Rp will be 200 Newton, and if Rp is 200 Newton, then from summation of Fy equal to 0, Rr will be 0. That's what I told you, na? This is 200 and this is 0. 0 means there is no load here. So let me remove this. So if I draw the bending moment diagram, what am I going to get? From P to Q, the bending moment will linearly increase, right? 0 here, then 200 into 0.5, 100. Then it will suddenly decrease, 100 minus 100. Before this point Q, just left of the point Q, it will be plus 100, just right, it will become 0. And then it will remain 0, right? Here if you calculate the bending moment, what you will get? 200 into 1 plus 200 minus 100 minus 100, 0. This is going to be the bending moment diagram. 0, 0, 100 Newton meter. Okay. So A is the correct answer. Yes. Now this is from GATE 2019, 2 marks question. All the bars in the given truss are elastic with Young's modulus 200 GPa and have identical cross section with moment of inertia 0.1 centimeter to the power 4, means E and I are given. Lowest value of P at which the truss fails due to buckling is. We need to find the value of P at which the truss is going to buckle. Okay. One is asking different level of questions. Are these questions of same level of GATE mechanical branch also? What kind of question is this? Same level means what? Sometimes I don't even understand what you guys are trying to ask. Strength of material is strength of material. It doesn't matter which branch are you from, whether you are from mechanical or civil or XC, aerospace, PI. The topics are slightly different in aerospace, okay, because in aerospace we usually tend to focus on columns, thin walled members, okay. But if you have a common topic, for example, let's say if you have deflections of beams, then deflections of beams is same for mechanical, civil, XC, PI, all these branches. No, the concept is same. The questions will be almost same. What is I don't understand why people say that, okay, if you consider XC strength of material is difficult, if you consider ME the strength of material is different in aerospace. Array, strength of material is strength of material. It doesn't matter which branch are you from. Just because you are from mechanical, when you were preparing, you might have studied the PYQs of mechanical. So now the PYQs of mechanical are comparatively easier for you. But when you try to solve the PYQs of different branches after your preparation, you might find it difficult. But that doesn't mean it is difficult. Chalo. Now, first of all, we need to see the forces developed in all these three members. Okay, we need to calculate the forces developed in all these three members. So if I apply method of joints, then this is joint A. This is P. For now, let's assume that the members are subjected to tensile forces. So if you are getting positive answer, they are subjected to tension. If you are getting negative answer, they are subjected to compression. Let's check which of these are subjected to compression. This is A. This is the angle 45. All these angles are 45. Okay. So first of all, FAB and FAC both will be equal. From summation of Fx equals to 0, FAB and FAC will be equal. From summation of Fy equal to 0 to FAB sine 45 plus P will be equal to 0. So 2 sine 45 means 2 by root 2 means root 2. So FAB and FAC both are minus P by root 2. Okay, both are minus P by root 2. Okay, then this BC. So let me consider joint C to check whether BC is also subjected to the compressive force or not. This is P by 2, na? This is subjected to compression. This is joint C. So if I apply summation of Fx equals to 0, FBC is equal to P and it is subjected to tension. So BC is subjected to tension means there will be no buckling in BC, but AB and AC both are subjected to compression and both are subjected to same force P by root 2. So you can consider any one member. So P critical in AB. Okay, pi square EI by LE square. So this will become P by root 2. Okay. What is E? 0.1, no sorry, 200 gigapascal, I 0.1 centimeter to the power 4. 0.1 centimeter to the power 4 means 1 centimeter is 10 mm, na? So 0.1 into 10 to the power 4 divided by, what is the length of each member? This is 10 centimeter means 100 mm. What will be this? This is 50 mm, na? This is 50, this is 50, this is 50 root 2. What will be P? Five five eight 309.136 Newton. Need to find it in kilonewton. $558.31 kilonewton. You're getting this 558.31 kilonewton. Okay. Chalo. This is from GATE 2010. A load P is applied to the free end of a stepped cantilever beam as shown in figure. Young's modulus is E. Moment of inertia of the two sections of length 2 meter and 1 meter are I and 3I. Ignoring transverse shears and stress concentration factor effects, deflection at the point where the load is applied at the free end of the cantilever is. We need to find the deflection at the free end. But the flexural rigidity is not same. So how do you find the deflection here? We can apply moment area method, or we can apply Castigliano's theorem. Both methods can be used. This is how much? 3 Newton. This is 2 meters, 1 meter, I, 3I. Okay. So let's draw the bending moment diagram here. So if I draw the bending moment diagram, then from free end to fixed end, the bending moment will be linear, right? What will be the bending moment here? This is 0. This is 6 Newton meter. This is 9 Newton meter, right? What we need to find? To find the deflection, huh? Okay. So let's say this is point A, this is point B, sorry, B, this is point C. So YA will be equal to, according to moment area method, I have to take the first moment of area of the bending moment diagram. This is the bending moment diagram. I have to take the first moment of area, okay, about point A, right? We'll take the tangent at C, so I will calculating the vertical deviation of A from tangent at C. So about point A. So the centroid, what will be the equation? AAB into XA bar divided by EI plus ABC into XA bar divided by, it is 3I, na? 3EI. Okay. So what is the area between A and B? It's a triangle, right? Half into base is 2, height is 6, and what will be this distance? What is this distance from centroid to here? It will be 4 by 3, right? 2L by 3, 4 by 3. This divided by EI plus area between BC, it's a rectangle plus triangle. For rectangle, area is 6 by 1 And from center to here, what will be the distance? 2.5. Plus for triangle, area will be half into base is 1, height is 3. And from here to here, what will be the distance? 2 plus 2 by 3. 2 plus 2 by 3 means 8 by 3. This divided by 3 EI. Tell me what is the total? 2 and 2 will be cancelled. 8 by EI. 8 by EI plus 3 and 3 4. 19 by 3. 8 plus 19 by 3. 43 by 3. This is the correct answer. 43 by 3. Yes, B is the correct answer. 43 by 3 EI. Yes. The three-dimensional strain-stress relation for an isotropic material written in a general matrix form is this: A, B and C are compliances which depend on elastic properties. Which one of the following is correct? This is based on generalized Hooke's law. This is known as compliance matrix. How do you get this matrix? In order to know that, you need to understand the generalized Hooke's law. Epsilon x is equal to sigma x by E minus nu sigma y by E minus nu sigma z by E. Epsilon y is sigma y by E minus nu sigma x by E minus nu sigma z by E, and epsilon z is sigma z by E minus nu sigma x by E minus nu sigma y by E. Similarly, gamma yz xz xy, gamma yz is equal to tau yz by g, gamma xz is tau xz by g, and gamma xy is tau xy by g. Now we can write this in matrix form. So you get this: epsilon x, epsilon y, epsilon z, gamma yz, gamma xz, gamma xy. This is equal to some constants multiplied by stress. Sigma x, sigma y, sigma z, tau yz, tau xz, tau xy. Okay. Now here you will get some constants. So it's a matrix of constants known as compliance matrix. Okay. Compliance is inverse of stiffness. So it will be 1 by E minus nu by E minus nu by E 0 0 0 minus nu by E 1 by E minus nu by E 0 0 0 minus nu by E minus nu by E 1 by E 0 0 0. I am just writing this equation in terms of matrix. Okay. 0 0 0 0, sorry, 1 by G 0 0, then 0 0 0 0 0 1 by, sorry, 0 1 by G 0, last 0 0 0 0 0 by G. This matrix is also a symmetric matrix, just like stress tensor and strain tensor. Now if you compare it with this equation, A is 1 by E, C is minus nu by E, and B is 1 by G. Now what are they saying? Which one of the following is correct? C is equal to A by 2 minus B, C is equal to A plus B by 2, C is equal to A by 2 plus B, C is equal to A minus B by 2. So how will you know? You know the relation between E and G, right? E is equals to 2G 1 plus nu, na? Can you write E in terms of A? It will be 1 by A. Can you write G in terms of B? It will be 1 by B. Can you write nu in terms of A and C? Yes. Nu is minus of CE, right? And E is 1 by A, so minus of C by A. Okay. So I can write it 1 by A is equal to 2 by B, A minus C by A. This A and A will be cancelled, so B will be equal to 2 into A minus C. So B by 2 will be equal to A minus C, or C will be equal to A minus B by 2. So which one is the correct answer? C, A minus B by 2. But in order to solve this question, you must know the concept of generalized Hooke's law, this, how to write it in the matrix form, and this is known as a compliance matrix. If you don't know this, you will not be able to solve this question. Okay. I think we have solved enough number of PYQs for today. But let me tell you, we are going to continue this series. Tomorrow you will have PYQs of some different subject. Okay. I think tomorrow is basic thermodynamics. Okay. Then day after tomorrow you will have PYQs of vibration. Then day after tomorrow, day after that, you will have vibrations of propulsion. Then PYQs of aerodynamics. So we are going to solve PYQs of different subjects. We are going to continue this series. Okay. This is my Telegram group. You can follow this Telegram group. Okay. And if you are preparing for GATE 2027, then we already have a batch of aerospace for GATE 2027. You can enroll in that batch. Okay. Thank you so much for watching this session. I'll see you guys in some other session.